Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to continue our conversation on intermolecular forces. We're going to do a quick review, and then we're going to go in a little bit further detail than what we did in yesterday's lesson. So the 5 types of IMFs that we have are ion-ion, ion-dipole, hydrogen bonding, dipole-dipole, and London dispersion. Okay, and what I want to do is I want to go through each one of these and give a quick example of the intermolecular force and how that intermolecular force can increase. So to get us started, we got ion. So basically, if you have 2 ionic compounds, the intermolecular force that exists between the two, okay, is going to be called ion-ion. Now, the way that we can increase this is by increasing the charge on these ions. So this is a positive one and a negative one. Well, if we had positive 2s and negative 2s, that would be stronger than the positive 1s and negative 1s, and that would increase the interaction. So as I increase the charge, I will increase the amount of ion-ion interactions that I have within the molecule, okay, or within the substance. Ion dipole is going to be something like sodium chloride interacting with a water molecule. Okay, so this is the ionic species. So it's ion. This is the thing that has a dipole moment. So that's the dipole part. Okay, the way we increase this is once again by increasing the charge of the ionic species, or we could increase the dipole moment of the dipole species. Okay, hydrogen bonding would be like water interacting with water. Okay, because remember, to have hydrogen bonding, you have to have hydrogen bonding with either nitrogen, oxygen, or fluorine. Okay, so the interaction in between the molecules is actually what we call hydrogen bonding. So hydrogen bonding is not a bond, it's an interaction that exists between molecules, of which we call intermolecular forces. How do we increase the amount of hydrogen bonding? 2 things. Okay, you could increase the dipole moment, or you could increase the number of OHs. Okay, an example of this would be like if I had a carbon chain, maybe something like this. The more OHs that I put on this carbon chain, the more hydrogen bonding I would have. Okay, so if the rest were just hydrogens, right? Okay, good. Dot, 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 dot. So the more of these I have on there, the number of hydrogen bonds I have, the more intermolecular forces I will have. So I can either increase the dipole moment or increase the number of hydroxyl groups in an organic compound. Dipole-dipole, an example would be like H2S interacting with H2S. There's no hydrogen bonding here because the hydrogen is not bonding with nitrogen, oxygen, or fluorine. So this is just an ordinary dipole-dipole interaction. The way you can increase that is by increasing the dipole moment. So things that are more polar are going to have a higher dipole moment. The higher the dipole moment, the higher the boiling point, which is our indicator for how much intermolecular force, or the magnitude of the intermolecular forces that we have. And then finally, we have London dispersion forces, which would be any type of compound. Actually, all molecules have London dispersion forces. If there's electrons, you can distort that electron cloud and you'll have London dispersion forces. The way you increase the dispersion forces, though, is by an increase in molar mass, which I'm signifying as capital M, capital M. Okay. Now, these are just the types of intermolecular forces. And when it comes down to overall intermolecular forces, it comes down to 2 things. It comes down to type versus the molar mass. This is the big idea that we're going to try to get across today in our video. Okay, so the 2 rules are: when the molar mass is significantly different, and what we're going to call significantly different is a factor of 2, and this is just a guideline. This is not a hard, fast rule, but it's good for introductory students to have kind of an idea of what type of factor we're talking about. But if there's a difference by a factor of 2, then molar mass is going to determine the magnitude, the overall magnitude of the intermolecular forces, or the IMFs. Now, if the molar masses are fairly similar, or what we call comparable, which is below a factor of 2, then it's going to be about the type. Okay, so more than a factor of 2, molar mass is the thing that's going to trump everything. However, if we're below a factor of 2, then the type of intermolecular force is going to be it. And we got like 4 problems at the end that are going to talk about this type versus molar mass. But before we get there, I want to take a look at just a few diagrams that was in our textbook from last night's reading. Okay, now if you're not in my class, this stuff is still kind of important to look at, so feel free to kind of like join along in our journey here. Okay, so what this picture shows is how the dipole moment is increasing. Now, the dipole moment is signified by the Greek letter mu. In this first molecule, there's hardly any dipole moment at all, okay, 0.1. This thing is basically non-polar, okay? But as we move to the right, the dipole moment increases to 1.3 to 2.7 to 3.9. So as you move to the right, the molecules are becoming more and more polar, which means that there's more of a positive side and a negative side within the molecule. And the more positive or negative you get, the stronger your IMFs are going to get. And the stronger the IMFs, the higher the boiling point is going to be. So you can see this is going to be the lowest boiling point. And as we move to the right, as the dipole moment increases, the boiling point increases as well. So that's just showing us that as you increase these dipole moments, okay, increase dipole moment, increase dipole moment, increase dipole moment, the IMFs are going to increase as well. And this is a great example of seeing that, okay? Now, here at the bottom, okay, is this chart, okay? And on the y-axis, it's boiling point, and on the x-axis, it's molecular weight, or kind of like molar mass. And what we're going to see is, if we go from right here to the right, we're going to see as molar mass increases, the boiling point increases. And that's going to be our London dispersion forces. Okay, so once again, as molar mass increases, London dispersion forces increases, and that gives you a higher boiling point. But what's interesting, as we go lower, it spikes here, and spikes here, but it goes down over here. Okay, and what this chart is trying to show you is how special hydrogen bonding is. Now remember, to have hydrogen bonding, you have to have hydrogen bonding with nitrogen, oxygen, or fluorine. And as you can see it, here's your oxygen, your fluorine, and your nitrogen. So nitrogen, oxygen, and fluorine were the things that have hydrogen bonding. And hydrogen bonding is a special type of dipole-dipole. And as you can see, the magnitude of the IMFs are increasing because the boiling point is increasing. Now, when the hydrogen just bonds with carbon, it doesn't spike up, okay? So remember, hydrogen has to bond with nitrogen, oxygen, or fluorine. Nitrogen, oxygen, or fluorine to be considered hydrogen bonding. So that's a very big type of IMF that we have in chemistry. So hydrogen bonding is pretty special. So this thing shows two things. It shows as we increase our mass, because of dispersion forces, boiling point goes up. But also, if we change types from dipole-dipole to hydrogen bonding, it spikes up. Dipole-dipole to hydrogen bonding, it spikes up. Dipole-dipole to hydrogen bonding, it spikes up, because when you go from this level to this level, it matters, okay? And then the last thing that I want to show you in the book, okay, is this idea of surface area. We got two compounds here, both C5H12s, okay? And this compound, it's in a straight line, okay? And in this time, it's a little bit more spherical. So it kind of, the pentane is balled up. It's not connecting in a straight line, okay? So this is where surface area is going to matter. You can see that there's all this interaction that can exist when it's in a straight line, the carbon chain, okay? You get all this surface area, all this interaction, that increases the intermolecular forces. Where if it's more spherical, the only area it can interact with is right here where it gets close to each other. So where there's lots of surface area, we get a larger boiling point, and when there's only a little bit of surface area, we get a lower boiling point. As you can see, these boiling points aren't dramatically different, okay, because they have the same molar mass, they have the same type of IMF. The only thing that's different is surface area between these two compounds because they're both C5H12s. Okay, so we're talking about dipoles, hydrogen bonding, and surface area with those diagrams. Now let's go ahead and get into some sample problems. In these sample problems, I'm going to ask you to do things during this video. So what I'd like you to do is I'd like you to pause the video and I'd like you to draw the bonding for these three compounds. And when you come back, we're going to talk about which one of these has a higher boiling point. Remember, that's the measuring stick in which we determine the overall IMFs, okay? So whichever one has the strongest IMFs is going to have the highest boiling point. And I want you to figure out, well, which one of these has the lowest boiling point, which one has the highest, and which one's in the middle. So go ahead and draw these out and then try to determine which one has a higher boiling point and a lower boiling point. So after pausing the video or unpausing the video, you should have the drawings that look something like this. Now let's kind of walk through this first problem, okay? What kind of IMFs do we have between these three? Because what I'm looking at, I'm seeing that the molar mass is about the same. And remember, when it's coming down to overall IMFs, it's always the difference between the type of IMFs you have and the molar mass. If they all have the same molar mass or similar, below a factor of 2, it's going to be the type that matters. All these molar masses are within a factor of 2. Nothing doubles anything here. Okay, so these molar masses are fairly similar. So which one of these is going to have the higher boiling point is going to be based on the type. Well, this one only has London dispersion forces. There's no dipole at all in this first problem. The second one does have a dipole. We got this fluorine here, so we have this difference in electronegativities. We get the dipole. They're not canceling out. And this one not just has a dipole, but we have hydrogen bonding. We have a hydrogen that's bonded with an oxygen, nitrogen, or fluorine, and that's going to be a special type of IMF. So I have a feeling that this one is going to be significantly higher than this one, but this one is still going to be a little bit higher than this one. So let's take a look at those forces. So London dispersion, they all have London dispersion because they have electrons, but this has dipole-dipole, and then this one has hydrogen bonding. So we got to go from the lowest type, which has the lowest boiling point. This one has a dipole-dipole, so the boiling point increases a little bit from -42 up to -38, okay? But this one's going to have a nice spike up to 78 degrees, and it's all because of the hydrogen bonding. So remember, when the molar masses are similar, it's going to be the type that matters the most. So this one, the highest type between these three, is going to be the hydrogen bonding, and that was that last molecule right here. Okay, let's take a look at another problem. Okay, let's look at number 2. So same thing. I would like you to kind of pause the video, draw these out, okay, and then try to figure out which one has a higher boiling point and justify your answer. If you unpause the video, you're going to come back and you're going to find out that these molar masses are actually identical, okay? The only difference, this is in a straight line, and this one kind of looks a little bit more spherical as a molecule as a whole because of the branches that are coming off. Well, a higher surface area should give us a higher boiling point, okay? This boiling point is -0.5, where this one's much lower at -12. So because of surface area, okay, because the molar masses are the same, the type is the same, they're both just, London dispersion forces here. So the only thing that's different between these two is surface area, okay? And this one has more surface area, so it's going to have the stronger IMFs, so it's going to have the higher boiling point because -0.5 is higher than -12. We go into our third example. Okay, so our third example, I'd like you to draw these two out, pause the video, and determine which one has the higher boiling point. Okay, when you come back, this is what you should have. Okay, if you look at these, they have the same molar mass. Okay, however, their dispersion force, their type of IMF is different. Okay, I have hydrogen bonding here, and there's no hydrogen bonding here. Remember, hydrogen has to bond with oxygen, nitrogen, or fluorine. I have it here. The hydrogens are only bonded to carbon here. Okay, so there's no hydrogen bonding here whatsoever. Okay, now there's a dipole, but these forces don't cancel out because it's not linear. When there's four domains, you get a tetrahedral shape. So this is actually going to look more bent. Okay, so we got hydrogen bonding here, and we got dipole here. Well, which one is higher between hydrogen bonding and dipole-dipole? Hydrogen bonding is higher than dipole-dipole. So I would suspect that this one has a higher boiling point than this one, 78 degrees versus negative 25 degrees. Okay. And for our last example, we're going to take a look at this one. Okay. So I'd like you to pause the video, draw this out, and then when we come back, we'll be looking at it. So after unpausing, okay, you should have something that looks like this, okay? Now, if you look here, okay, at this compound and this compound, or this molecule versus this molecule, we know what this one is. It was used in the previous examples. We know this is 78 degrees Celsius, but look at their molar masses, okay? I know this one has hydrogen bonding, okay, but this one has, and they both have dispersion forces, but look at the molar mass. It's 100 versus 46. Okay, and if you remember, when it comes to the overall IMFs, which determine the boiling point, it's always between type and molar mass. And when the molar mass is significantly different, more than a factor of 2, it's going to come down to molar mass. So if that's true, I expect this to have a higher boiling point than this one because it's more than a factor of 2. Just barely, but it is a factor of 2. And when we look at the boiling points, this has a boiling point of 98 degrees, and this one has a boiling point of 78 degrees. So I hope this information was helpful. If you found it helpful, please give it a like and subscribe, and even leaving a comment will help push this information out to other students that are interested in learning chemistry.